And you're very kind, Kaz. I insist it's my fault, but okay, wait, more people are coming. Okay, we're going to start in a second. I know, so it's going to be a short class today.
Hello, hello. All right. Hello, Vivian. Hello, Charlie. Hello. Good morning, Alyssa. Good morning, Vivian. Good. Right. Thank you for the video. That is awesome. Thank you, Charlie, for the video. That is awesome. Oh, and you can hear me, right? I think Vivian can hear me, right? You can hear me. Maybe you can't. Wait, can you guys hear me? Oh, yes. Oh, yeah. Okay. Thank you. Thank you. Okay. Oh, and so oh, a lot of good mornings. Okay. And well, okay, wait. Okay. One day I will not be a spaz. And then I'll probably have to shoot because no one would recognize me. Okay. Wait. So thank you for the yeses. Okay. Good morning, Alyssa. Good morning, Vivian. Good morning. No, starting again. People coming. Whoa. Okay. It's been a long time since we. Okay. Good morning, Alyssa. Good morning, Vivian. Good morning, Lakshmi. Hello, Daniela. Thank you for the yes, Alyssa. Thank you for the yes, Vivian. Thank you for the yes, and the yay, Charlie. And hello, Charlie. And okay. Oh, yes. Okay. And Charlie said, thank you for the video, Charlie. And thank you for the picture, Farouk. And hello, Farouk. Okay. That's a hello. Okay. We're going to start in a second. Well, I feel like it's a small group. It's a small group plus 11,000. No, I totally appreciate anybody who is watching this at all. One thing to quickly, okay, we're going to start in a second. Okay. We are going to go where we're going now. Where are we going now? It's been a long time. We didn't have class wait, no, it hasn't been a long time. I mean, it has. It feels like it has, but wait, why does something feel strange? No, right. We didn't have class Monday. Right. It has been a long time. Okay. So what we're going to go back to is average acceleration, like the concept, the application, the implications appertaining thereunto. And we're specifically going over average acceleration in the context of homework 4, which I may or may not pull up in a second. Well, I will pull up in a second. It kind of means that pretty moment soon I'm going to put in a homework 5 for next. Oh, no, I did already. What am I saying? All right. Anyway, we're going to talk over homework 4. Even if you haven't done it yet, you can still do it. Blah, 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 blah. Okay. Clearly, I need to get my head together. Okay. We're going to start in a second. I'm stalling. I have noticed that I tend to talk more the less I have to say, and I tend to talk faster the less I have to say, because I'm in a rush to convince you that I have something to say. Okay. Oh, and hello, Julian. Good to see you. Okay, thank you for the video. Okay. We are talking about, you know why I'm stalling this, because I'm trying to get the screen share going. I would like to put up the homework for a second. I apologize. But we are talking about homework 4. We are talking about average acceleration. The definition of it is right there on the board. It has implications. It is a vector equation. Direction does matter. I am looking for the sheet. I am a bad person. Here we go. Okay. Here we go. Okay. Yes. Okay. Just because it's been a while and just for perspective, what we're talking about is this sheet, this homework sheet, which again, if you've done, I've not given back yet, and I appreciate that you've done it. If you haven't done it, you can still do it. We were up to, okay, the first question on the sheet was like a review, just to make sure we were still clear on the difference between vector quantities and scalar quantities. Now, the second question on the sheet, and this is what we were going over right before you even did the sheet. Now you've done the sheet. The second question on the sheet, and tell me again if you can't hear me or if you're not seeing the same screen share that I think you're seeing. I believe we're looking at problem number 2. That the problem is called instantaneous velocity. Okay, and it's asking something about instantaneous velocity, and it is not supposed to be a trick. It's not supposed to be a trick. In some ways, getting the answer to this particular question, it might be almost as simple as you might think, and that's good. We're partly getting it like we always do in physics because we're going to build off of that and get some other things. But also, the reason we're asking this question, I just want to establish, or the reason we have to focus on this concept, this seemingly new concept of instantaneous velocity, is that everything we have said about velocity up until now, everything we've said about velocity or speed for that matter, has been about average velocity. We have defined, and we've talked a lot about averages, and we're talking about the nuances of that. Average velocity doesn't always mean the average of velocities, or at least it doesn't seem like it always means that. But whatever it is average velocity, which means how the displacement covered throughout some interval of time. Like average velocity has necessarily meant until this moment that there was some finite region of space traversed between 2 points in space during some finite region of time that transpired between 2 points in time, right? Like literally and significantly, average velocity assumed finite segments of space and time that were being divided by each other to get an overall average that signified something about that entire region of space and time, but may or may not have signified anything precise about any particular point, any particular instant, or any particular position in that region of space and time. Now, the definition of average acceleration, if I turn back to the other sheet for a second, which I guess I will in a minute, if you look at the definition of average acceleration, it's modeled after the definition for average velocity. I mean, it has exactly the same format. That's what we were saying last time, the exact same structure, that definition. So on the left side is an average on the left side of the equation, but on the right side is the difference between 2 velocities that seemingly occurred at particular points in time and space, right? Like average, oh, someone's here, sorry. Average acceleration, like A with a bar over it, triple equal sign, V minus V naught over T. And the key point I'm trying to make right now while I let somebody else in is that you got to notice that the V, how can I let someone in? The V's on the right side of that equation are not V bars. Like the V's that are on the right side of the definition of average acceleration are not average velocities. Average acceleration is not the difference between 2 average velocities over time. It's the difference between 2 momentary velocities, or what we strictly call in physics, 2 instantaneous velocities per time, right? And on the one hand, I hope that sort of does make sense. And on the one hand, I hope everybody can picture this concept of an instantaneous velocity. Let me say again, instantaneous velocity is presumably or purportedly, or it is largely speaking, is what the cop pulls, and I say this with all due respect to John Jay, the cop, the officer of the peace, pulls us over for on the highway. If one of our trusted one of our trusted colleagues at John Jay, or if an officer of the peace were, God forbid, to pull me over as I was driving down the road because of some misunderstanding in the universe where accidentally for some moment it appeared as though perhaps I had unwittingly or for some deep justified reason had like broken the speed limit, right? When the police officer pulls me over and says, do you know how fast you were going just there by that school zone? I'm a physics professor, but it would therefore be a major mistake for me to turn to the police officer and say, well, that's an interesting question, sir. I've been traveling for an hour, and in that hour, I've covered only 15 miles because I took 2 bathroom breaks and like my car didn't start for the first 10 minutes and blah, blah, blah. I've traveling for an hour, and over that entire hour, I've only traveled 15 miles. So I guess my average velocity was 15 miles an hour. So I guess I was going 15 miles an hour. So I don't really see what the problem is, officer. Like that would be a hideous mistake of judgment for me to say all of that to a police officer, and especially in that tone of voice. But it would be, I want to make it clear, it would be a hideous bad judgment to say that to a police officer, even if it were all exactly true. I hope everybody understands that. Even if it's strictly true that for the past entire hour, I've only covered a total of 15 miles, right? And even if it is therefore true that over that hour, then my average velocity is 15 miles per hour, that in no way tells anybody how fast I was going a moment ago when I passed the school or passed the cop car or whatever, right? Like I could have been going any speed at that moment. I could have been going incredibly fast. And how is that not a contradiction? Because for the rest of the hour, I was going incredibly slow and it averaged out to 15, right? Or I made 2 pit stops or blah, 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 right? In other words, the average for some interval is not the same number necessarily as the velocity at some moment. And the velocity at some moment is such a meaningful real to world concept that sometimes it's all we care about, right? The cop does not care and shouldn't care about my average. Well, I mean, maybe they should care in some statistical way, but like I don't get pulled over for average velocity. I get pulled over for the instantaneous velocity, supposedly, that I would have as I pass through a radar gun or as I pass the cop car, or as I pass some point in space, and it is some point in time, right? I mean, I think that's clear to everybody. I hope, right? So, you know, instantaneous velocity is a real thing. Often it's the most real concept in anybody's minds. However, I'm saying all this on the one hand to say, okay, there's this thing called V without a bar over it. I think we all know it from real life. But at this point in the class, it's all of a sudden getting introduced on the right side of the average acceleration equation. Like never, pardon me, someone else is here. I just want to make clear again, like I feel like we all know that this thing is real from life, but I've never given you an equation for it. I've never given you a way to solve for it. We've never done any problem, and that's not an accident, but we've never done any problems solving for instantaneous velocity. We've only done problems, and the only thing the definition can give us, and you need to know this on exams, like that definition that we have only solves for average velocity. But suddenly we need instantaneous velocity because we need to compare 2 instantaneous velocities. I know I'm ghostly going in and out here. This is weird. I'll do something in 1 minute about that. I'm probably switching sheets too fast, but the reason that the question on the homework here asks about instantaneous velocity is because it's assumed that we have some concept of that on the right side of the average acceleration definition. It assumes we would know 2 velocities and subtract them and divide by the time interval between in order to get acceleration. So how do we get instantaneous velocities? That's the question, right? And the answer is a bit complicated. So this first question is a question in how to get it in a comparatively straightforward context to see if we can figure anything out from that. Because truth be told, there is no one easy equation or easy way to get instantaneous velocity. It depends on the context, right? I'm going to pause for a second because clearly I'm like turning into Casper the Friendly Weirdo here. So let me just like pull a shade or see if I can do something about the lighting for 1 second. I don't know if that helped. I think that helped. Okay. So I'm babbling. What I want to do now, I'm going to solve this problem that's sitting right here. So I'm going to switch the screen. Okay, that's why I'm stalling again. I'm going to switch back to the pad. I'm going to just solve this Roman numeral 2, and again, you may have gotten the answer, or probably many of you did. Some of you might even get the answer just looking at the problem and reading it right now for the first time. You might be able to get the answer in your head. I want to call, and if you have an answer sitting in your head, you're probably right. It's not a trick, but I want to show you something about that answer, and I want to caution you again. This will show you how context leads us to the notion of instantaneous velocity, but not all contexts are the same, and not all contexts are as straightforward as this one. Okay, so the concept here, I mean, the example here is a car travels at constant velocity for 30 minutes. During that 30 minutes, it travels 40 miles. What's the car's instantaneous velocity at precisely the 18th minute and 42nd second? Okay, so I'm going to switch screens. Actually, okay, I'm going to, pardon me for a second. I'm going to write it first while I'm looking. I'm just copying this down. Obviously, if there's any questions, please chime in. Okay. Okay, so I think, here we go, switching screens. Okay, what you should see. I don't know what, okay, what it's coming. What, I wish I could do this in an actual classroom, just like make things appear. Okay, so there, I guess that would be called a PowerPoint. Yeah, okay. So here's the question, right? Now notice I've written out the question. I probably should draw a diagram. Okay, here's a diagram. Here are the facts of the problem, right? The car's traveled for 40 miles. It's traveled 40 miles in 30 minutes, which I call half of an hour, right? And what we want to know is at the 18th minute, 0.7 seconds, did a little unit conversion, like I think it said 42 seconds, right? But 42 seconds, if you think about it, is 7/10 of a minute, if you think it through, or 70% of a minute. Sorry. Anyway, you can think that through. But and then the question is, what is the instantaneous velocity right at that moment? Now, again, what I'm emphasizing, okay, so I don't think we have a direct equation for this yet. Okay, and if this were a problem on an exam, if I just literally wrote V equals like 40 divided by 30, I would probably end up with the right answer, but for the wrong reason. Let me, if I don't know what to do here, a person can't just randomly walk in and say, how fast were you going right then, unless you know. I'm not making sense. What I'm trying to say is, I always want to start with something true and move to something relevant rather than the other way around. So I could, if this were an exam or if this is life, in order to solve this, I have to start with a general principle or definition, right? Or general definition or principle. Just like here's my diagram and fact pattern, and here is the question that I'm asking. What is the question? After I ask the question, I have to write down a general principle or definition. So I might do that. I don't have that many general principles or definitions to work with here yet. I have the general definition or principle behind average velocity. Okay, so I would write it down, and sure, I would probably say something like, okay, I would take my space and divide it by my time, and get something like this. And you might be thinking, well, that's the answer. And I'm thinking you're right, that is the answer, but I'm not going to circle it yet. And here's why. It's not the answer yet. Like, what I want to make very clear is what I just figured out right here by dividing the displacement over time. What I just figured out right there is the average velocity, right? That's what that is. That is the average velocity for the entire trip. That's the thing that if I start babbling about to the cop, I'm really off on the wrong subject, and I'm really not helping my case. If I just say that, that's my average velocity. There is no guarantee in life that average velocity for a whole interval is the same as instantaneous velocity for every moment in that interval. Just like if your average in a class is 85, it doesn't mean that you got, that I know what you got on the third exam, right? Unless I'm specifically told, as I am here, if I'm specifically told the key fact that I wrote right there, which in English, it said, a car travels at constant velocity for 30 minutes. What I'm trying to emphasize here, probably making too big of a deal of, but what I'm trying to emphasize here is that's actually the key piece of information in the problem. All the number facts themselves don't mean anything and don't allow me to finish this problem unless I was told, and I'm not even saying it's always the case, but here I was told the car is always going at the same velocity. And the mathematical way to write that is, oh, in fact, I could even write, I even probably should write it like this. Like, I was told that whatever velocity the car has at the beginning, V0, its initial velocity, is the same at every step along the way. I was told that the car never changed its velocity. And that's a key fact, and I could write it mathematically that way. Therefore, once I figured out the average velocity, I can now say, wait, go to the next page. Okay, I'm belaboring this point. I am belaboring this point. I'm trying to say it's another one of these tricky but not tricky, tricky but not tricky, tricky, not, but tricky kind of things, where I'm saying what I'm trying to drive in here is, by definition, average velocity and instantaneous velocity are not the same. Triple equal sign, they do not mean the same thing. And we shouldn't assume, therefore, necessarily that they always work out to be the same. Don't use one equation to get the other. If you are on an exam and someone asks you what's the instantaneous velocity, and you just divide a displacement by time and just write that number as your answer, you'd be lying and you'd like lose points if it were an exam. However, and next step, we get instantaneous velocity from context. We have to know something. We can't just know the average velocity for an interval. We have to know something further about that interval in order to infer the instantaneous velocity from the average. In this case, this is meant to be the simplest possible case of all. In this case, what we were told is, all right, we have this average for the whole interval, and guess what? Whatever the instantaneous velocity is, it's never changing. It's a flat line. It's a horizontal line if we put it on a graph. If we put a graph of velocity versus time, it's a horizontal line. So if you get like or I should even say on a position time graph, we have a horizontal line. So if you get the slope for any section of the graph, you have the slope. If you get the value for any section of the graph, you have the value for the whole graph itself, is what we're saying. Therefore, in this case, if you have the average for the whole thing, then we can say the instantaneous is the average in this case, and the answer is 80 miles an hour. I'm really belaboring the point, but I'm trying to say V does not triple equal sign V bar, but in this case, it does. Okay, that's way too. Let's go to the next problem, because I think you all get that. Well, actually, no. Like what I'm really trying to say here with this example, we were able to figure out how fast the car was going at this moment because we knew its velocity in general, and we knew something about the pattern or the rate of change or the lack of change in its overall velocity. Like if it had been one step more complicated, and this is what we're going to get to, say it had been one step more complicated, say the velocity were changing as this car went, right? Say it started from rest and it was getting faster and faster and faster. We could still, then that would be a harder example, right? But we could still figure out how fast the car was going at a certain moment, even though it was a different velocity every moment, as long as we had a pattern or rule for what was happening to the velocity throughout that context, right? Like here, we had a pattern or rule that was so simple. It was that the rule is it never changes at all. So as long as you know the thing for overall, you can figure it out at any moment. If the rule were just one step more complicated, like, okay, imagine the velocity is changing, but it's changing in this patterned way. Imagine if every second you gain 5 more miles per hour of velocity, or every hour you gain 5 more miles per hour of velocity, then we still be okay. It would be one step more complicated, but we would still be okay. We could know the velocity anymore because we would just use that pattern. Like at the beginning it was 0, and then 1 hour later it'd be 5, and then 1 hour later it'd be 10, right? Even if there's changes, we can figure out what's going on as long as there's something about the change that doesn't itself change, right? That's what we mean by a pattern or a rule or an equation or a derivative. In this case, in other words, what we're saying is you can figure out how fast things are going at any moment, even if they're changing their velocities, as long as there is a constant to describe how they're changing their velocities. That is called acceleration. That is what acceleration is. Acceleration is the rate at which you change your rate.
right? That's what it is. It's the rate at which you change your rate. If velocity is a first derivative of position with respect to time, to use calculus language, then acceleration is the derivative of that. It is the derivative of position with respect to time. It's the second derivative. It's the pattern of the patterns. And as long as we have one, we can figure out the lower pattern and the lower thing from that. Yes, yes. So that's what acceleration is all about. It's the pattern of the pattern. It's the rate. It's the constant rate at which something is not constant. So that's sort of like the point of that example. This still doesn't give us an equation for instantaneous velocity. We'll get to that, but it gives us a way of understanding. They're both intertwined. It gives us a way to see both. All right, so we're going to go to the next example. No, we're just going to keep going. But again, stop me with questions. Okay. Oh yeah, and when it says your textbook anywhere in the, oh, you can't see the question. I'm sorry. So the next question is this. The question is, okay, I have a Yabber bounds. Okay. Okay, so here's the question, right? I have a 1975 Toyota. It can go from 0 to 60 in 2 minutes. Let's just even talk about that statistic for a second. Like you hear this in car commercials, or we used to all the time here in car commercials. They would say like the new Maserati can go from 0 to 60. And then right now, let's pause for that for a second. Go from 0 to 60. Okay, like that means change velocity from 0 miles per hour to 60 miles per hour, right? I mean, like in this case, speed up, increase your velocity from 0 miles per hour to 60 miles per hour. That's a description that we're making of some kind of car. Now, if that's a change in velocity, but notice that is not good enough. That is not enough information to express the acceleration of a car. Any car, presumably, any car that can ever go 60 can go from 0 to 60. When you go from 0 to 60, when you change from 0 to 60, that is a change in velocity. But that numerically does not tell you enough to know the acceleration. You have to complete the sentence. Like it can go, the new Maserati is amazing and you want to buy it and it has a really strong engine and it costs a lot of money because it can go from 0 to 60 in 1.3 seconds. Like that's their point, right? Like that in such a small amount of time, it can increase its velocity by so much. The less time it takes to change its velocity, the smaller the denominator of a given fraction, the bigger the whole fraction, the bigger the rate is, the more powerful we think this engine is. Now, so I have a Toyota, right? 1975, I was 5 years old in 19, but I had a 1970, whatever. In 1986, I had a 1975 Toyota. It could go from 0 to 60, but like it was a piece of garbage. And so it took a long, I mean, this is obviously an exaggeration, but it took a long time to rev up from 0 to 60. And while it was revving up from 0 to 60, it was presumably traversing somewhere in space. Like it wasn't like a Flintstone mobile, like revving itself up while sitting in my driveway. right? So imagine that this car takes 2 minutes to go from 0 to 60. Now that's enough numbers to give us an acceleration rate. How do we express here in this question, it's asking to figure out the acceleration rate. Now it's asking for the acceleration rate in certain units which do make sense for this problem. It wants me to figure out the rate of acceleration in miles per hour per minute. Right? Notice there's 2 references to time. That makes sense because velocity itself is displacement per time, but acceleration is change in displacement per time, right? So in other words, we're figuring out acceleration. Here we want to know the acceleration. It's change in velocity per time. So in this case, like V naught, the original velocity is 0. The final velocity is 60 miles per hour. And these are not metric units, but that's okay. Per time, the time is 2 minutes, right? Now, in this case, in this particular question, it wants me to solve in literally those units. It doesn't want me to do any unit conversions. It wants me to just actually see what I get in the units that are presented. So sure, if I do, I get exactly what you would think. It's not meant to be a trick. I would get 30 miles per hour per minute. That's my average acceleration. And that is the answer. That is an answer. And I want you to understand that that's a valid answer, especially it's the only valid answer for what this question is actually asking. Now it looks a little bit, or you could write it, by the way, you could also write it like this. Like you could put, I mean, both of those time units are in the denominator. They're both, it's mile, right? They're both in the denominator. Neither one of them sweeps up. So it's miles per hour per minute. That is valid. There's no rule that says that all the time units have to be in the same type of time units. There's no rule that says this has to be metric. The reason we're leaving it that way for a moment is because maybe it looks awkward, but on the other hand, I actually think that writing it that way gives me the most intuitive, direct understanding of what I really mean by acceleration. What I really mean by this number is if it keeps up this rate, right? This is an average. This is an average. But if we keep this up, then that means every minute we're getting faster by 30 miles per hour, right? It doesn't mean just to be as clear as possible. One of the reasons I'm leaving it in these funky units, and again, I know many of you have taken physics in high school, or taken physics before, you're used to seeing the units written a different way for an acceleration, and we're going to do that next. Those other ways of writing the units have their advantages, but this has its advantage as well. And neither one is like right or wrong. What this is trying to express to you, it's trying to, by having the 2 time units, like 2 different ones like that, I'm really trying to get across what role each of the time units is actually playing. What I'm really trying to get across right here before I go any further is this acceleration rate, which is the answer to this question, right? Like that car on average is accelerating at a rate of 30 miles per hour per minute. Like, you know, you can say it that way, 30 miles per hour per minute. Or if you want, you can say, if it's easier, you can say 30 miles per hour every minute. You can say that. What we're not saying, this is very different from saying 30 miles per minute. Like that's what we are not saying that every minute this car travels 30 miles. Like we're definitively not saying that. We're going to start doing problems soon where we're going to ask how far the car did travel. And the answer is not like how far did it travel in a minute? The answer is not 30. And we're going to ask how far did it travel in 30 minutes, in 3 minutes? And the answer is not 90. Okay, what this thing is saying is that every minute, the speed has traveled, has increased by 30 miles per hour. What this is really saying is that if we watch the needle on our speedometer, every minute that needle has traveled another 30 miles per hour on the speedometer thing, if you follow what I'm saying, okay? This is a rate of change of speed. It is not a rate of change of space advancement, okay? So it means every minute at this, I've increased by 30 miles per hour, which means like in 3 minutes, what can I say? I can say that at this rate, if I keep going, in 3 minutes, I would be traveling at a rate of 90 miles per hour. That's what I could say. And then you might say, well, doesn't that mean you traveled? I mean, then didn't you travel 90 miles? Well, no, because for one reason, I just said in 3 minutes, right? And we're traveling 90 miles an hour at that moment. We didn't travel for an hour. We only traveled 3 minutes. So we didn't travel 90. You see what, and there's other factors as well. Also, we weren't traveling 90 miles an hour the whole time. Only right at that last moment do we arrive at an instantaneous velocity of 90 miles an hour. So this is an acceleration rate. It is not a velocity. It has 2 time references in the denominator on purpose. Okay. Now, you might say, well, okay, but that's a little awkward. Like, why is it hours and minutes? Can't we get like some consistency going on here? Sure. If you want consistency, we can go to the next question. You asked for it. In the next question, let me just look at the sheet. The next one. Right, so B. Okay, so this is now 3B. So same givens. But now we want in miles per second, what is the average acceleration? Okay, that's the question now. Now this starts to look more like what you might be used to physics looking like or whatever. Now, granted, if it's really standard physics, it's probably going to be in meters, not miles, but you know, most cars in America on the highway we're used to miles per hour on the highway. So I'm just trying to be intuitive here for the moment. But what I am going to try to do is convert all those time units to something consistent. I'm going to try to convert the hours and the minutes all to seconds so that we have the same time unit in the denominator. And by the way, I'm going to go a step further in saying, once we have the same time unit in the denominator, then we can say, I just want to say right here and now, before we go any further, it's true. And by the way, someone in this class, I think it was in this class, it might have been, someone pointed out like weeks ago, like, aren't your unit, I was doing some problem with velocity and someone said, wait, shouldn't your units be meters per second squared there? And the answer happened to, at that point, been no. But there's at least one person in one of these classes who has seen meters per second squared before, or miles per second squared. Many of you have probably seen, again, in a high school physics class, or somewhere, you've heard of space per time squared. And yes, indeed, from here on in, most of our accelerations are going to be measured in space units per time units squared. But I'm trying to show you right here now, don't think of time squared as some mystical or weird or just like arbitrary black magic physics person thing, like, oh yeah, second squared, you know, those physicists, they're like always talking about things like second squared. Like, no, it's not arbitrary. And it's not just some weirdness that you should just black box in your mind. And it's also not some psychedelic fascination. It's not like we're squaring time. It's Michael J. Fox and a flux capacitor. No. We're just saying it's space per time again. It's rate of space per time changing per time. So there's 2 references to time, both in our denominator. They're both in the denominator. They're being multiplied by each other ultimately. So shorthand for second times second is second squared. That's all it means. It's not some weird version of time. It's just second squared, but it will be from now on second squared, because if you're talking about acceleration, there must be 2 references to time, one from the velocity and one from the change. Okay, so we're going to convert to make it consistent and have an easier way of writing it. So this is like a practice in awkward. This is a practice in unit conversion, and nobody enjoys unit conversion, and everybody's had it coming out of their ears in chemistry and whatever. But the thing about this one also is it's really like simple. I mean, it's just like seconds to minute. It's not like crazy Planck's constant or something. But because everything's in the denominator, it does sort of test your mettle. Like you have to be pretty okay and solid with unit conversions to be comfortable with doing it in the denominator and stuff. So I'm going to do it once with you to show you my way and sort of get us comfortable, hopefully, or bore you to tears. So we have miles per hour. Oh, and I'm saying 60. I don't mean 60. I mean 30, right? I'm sorry. Now we're trying to convert this into seconds, right? So what I'm going to do, first, I'm going to take those minutes. I'm going to convert them to seconds. I'm going to do this piece by piece. I'm going to convert the minutes to seconds, and then I'm going to convert the hours to minutes to seconds. Okay, I have everything in seconds. So how do I do this? What usually happens to a lot, and again, I want to be a little bit careful because things in the denominator, and that's where people get confused. When you do, there's different ways to do unit conversions. But here's my advice for doing unit conversions is most people know there's 60 seconds in a minute. Most people know that the next step is going to involve the number 60 somehow, I think. Where people get all thrown off and frustrated is like they never know whether to divide or multiply. And especially if something's in the denominator, it gets confusing whether you multiply by 60 or divide by 60. There are a couple of tricks for knowing how to do that. But here's my advice is what I do is I always multiply. I always multiply. I never think about dividing. I always multiply, and I always multiply by the well-chosen one, the well-chosen one. Meaning I always multiply by some number that equals 1, because that's what you're allowed to do, because if you multiply by 1, nothing changes. So I always multiply by some fraction where the numerator and the denominator are both two ways of saying the same thing. Like, because 7 over 7 is 1. 8 over 8 is 1. X over X is 1. X plus X over 2X is 1, right? Like, as long as the numerator and the denominator ultimately mean the same number, then the whole thing equals 1, and then you're allowed to multiply it. So what I always do is I turn my unit conversion thing into a well-chosen one. I know that 60 seconds and 1 minute are the same thing. So I'm going to make a fraction I'm going to put 60 seconds either in the numerator or the denominator, and I'm going to put 1 minute either in the numerator or the denominator, and I'm going to multiply by this fraction. The only question is which one's numerator and which one's denominator, which is really a sneaky way of saying, am I dividing or multiplying? But the way I make that decision is I just make sure that the units I want to cancel do cancel. In other words, I'm going to go like this. I'm going to say, I know 60 minutes equals 1. Sorry, no, I don't. I know that 60 seconds equals 1 minute, right? 60 seconds equals 1 minute. So I'm either going to do 60 seconds over 1 minute, or I'm going to do 1 minute over 60 seconds. How do I know which? Well, I know I want to get rid of minutes and convert to seconds. So I'm going to put the minutes on top so that they cancel with the minutes that are on the bottom. I'm literally going to go like this. 1 minute over 60. Now, again, I know some of you are like, are you kidding me? Unit conversions, I did this in 7th grade. Can you please go on? Some of you. But of those people who are like, are you kidding me? You're going to do a unit conversion now? Like, if there's one thing I freaking know, it's that. Of those people who are thinking that right now, I do apologize, and I'm sorry, but I'm trying my best. No, but of those people, some of them are thinking that, but actually they're wrong, and they get them wrong 1 out of every 5 times and don't realize that they're getting them wrong, and right? And others of you may hate them because you've never been able to get them right. And I'm telling you now, one way to do it, it makes it a lot clearer for me. It took me a long time to realize this, is I just always multiply by the well-chosen one. And I decide it by looking at what needs to cancel. Minutes need to cancel with minutes so that I end up with seconds. So that's just how I made the decision to put 1 minute on the top and 60 seconds on the bottom. I didn't think about, am I dividing or multiplying? I just arranged the fraction so that the units cancel, right? So I have that. Now, and before I do the numbers, I'm going to do it again. Whoops, sorry. Then I'm going to do it again. Right, so, well, I'm just recopying that. So now I have 30 miles per hour times second, right? Because the minutes canceled, right? And the one, sorry. Well, here, actually, okay. So I have this so far. Right? I hope I'm not, right? So I'm just following my own. So now I have to convert the hours into seconds. I could do it through minutes. I could go hours to minutes to seconds, or maybe, since I'm probably boring some people, why don't I say, I think we know there's 60 seconds in a minute and there's 60 minutes in an hour. So I think there's 60 times 60, 3,600 seconds in an hour. Stop me if that's unfair, if that's too fast, but it seems to me I could say there's 3,600 seconds in an hour. So I'm going to do that. I'm going to say 1/2 miles per hour per second times the well-chosen one. There are 3,600 seconds in an hour. I'm trying to get rid of the hours and leave seconds. So I'll put the hours on top. I'll put 3,600 seconds on bottom. The hours will cancel, right? And so now I have 1/7,200 miles per second squared, which, if I do that, that's a very small number. That's a very small number, right? It's 1/7,200. And that's like, well, you could say it like this. It's a very small number. I could say it like this, 139, which is so small and so annoying. How small is it? It's so small that when it sits around the house, it really sits around. That doesn't even make sense. Okay. But it's so small that I'm actually now going to use, there's a little practice in science. That number is so awkward to write. It's so ridiculous to write that many. To me, it actually calls for scientific notation. Like, this is a chance where I think scientific notation actually makes things easier, not harder. I mean, I think that is approximately 1.39 times 10 to the -4 miles per second squared. And I think that is the answer. Thank God. And again, for those of you who are like clawing your way out of your seat because you're so bored or because you got this answer like 400 years ago, I commend you. And that's cool. And at least your life isn't hard right now. At least it's only boring. But I'm also going to do a quick spot check too. Like, I'm trying to show how unit conversion, if you just go methodically, even when things are in the denominator, even if if you just always multiply by this one well-chosen one, I think it works out. But also the other thing is, since again, what I really secretly, but it's not a secret, what I really believe is that the reason a lot of people just don't like unit conversion because they think it's like annoying and stupid, but that's really what's going on, is they really are not comfortable or confident with it. The reason they're not comfortable or confident with it is they never know whether to multiply or divide. And the other way to know, and what I'm really saying is, now I can like step back and do a quick like intuitive check on this. Like, look, like we were measuring in hours and minutes before, and we're trying to convert to seconds. We're trying to figure out every second how much you change your velocity by. Well, if you're taking full minutes, if you're taking 2 minutes to change your velocity by a certain number of miles per hour, like you're changing it by a lot less every second, right? And if in every minute the car was traveling a certain rate in miles per hour, but you're trying to find out what rate it would do in miles per second, it's going to be a lot less. Like, in other words, what I'm saying is, if we just step back just to know, was it really right that I divided by 60 and I divided by 60 and was it really right that I divided by 60 and then divided by 3,600? Looking at my answer, I actually think, yes, it was right, because I'm getting a tiny, tiny answer. And that actually does make sense if I originally was expressed in miles per hour per minute. Every minute, this thing gains 30 miles per hour. But I want to know every second, how many miles per second does it gain? Well, like a lot less, a lot less, right? Every second, it only gains a certain amount of miles per second. How much? This much, 1.39 times 10 to the 4th miles per second squared. That's the answer. Bottom line of this whole, like, I took too long to do this exercise thing, is note the advantages and the disadvantages of the two ways of doing the units. First of all, both ways have time referenced twice in the denominator. No matter how you slice it, it's either miles per hour per minute, or it's miles per second squared. Either way, time is being referenced twice. In one way, I think the number you get is a lot more intuitive, like 30 miles per hour every minute. Like, Can you see that? Every minute it's going 30 miles an hour faster. So the number is much more intuitive, but the units are like miles per hour per minute. What the heck? This one, the units are all nice and tidy. Miles per second squared, miles per second squared. But then like you get this crazy number, and also like who can picture a second squared? So there's advantages and disadvantages to both, but that's the answer to that. I'm going to move on. But please stop me if there's questions. No, they're like, please move on. Like, please, really, really move on, please. Okay, I am. What's the next question? Oh. I'm actually going to skip around for a second because this is so, because I know I'm boring people so much. Oh, well, yeah, I'm actually going to skip around for a second. I mean, number 4 and 5, I'm looking at the sheet. Number 4 and 5 are important, very important. I may go back to them. Well, no. Okay, the next 2 questions on the sheet were very much about direction, slowing down, speeding up. Do I want to give me one? Okay, the next 2 questions are about the importance of direction and acceleration. I actually spoke a lot about this last time. We probably will have to go back to this, but right now I just want to summarize. I'm not going to go over the next 2 questions right now, and I'll see in your homeworks whether you know there were issues or not. But the main point of the next 2 questions, of the question 4 and 5, and I know you're not, well, actually, okay, no, I'll do it like this. Here we go. Hold on. I will share the screen. Give me a second, just so you can. Okay, I'm going to try to do this because we go till 12:05. I'm going to try to do this sort of in English. I don't want to, if I start writing a ton of things down for this, I'm going to go too slow again, like I kind of just did. So hopefully you can see on your screen. Can you see? Yeah. Okay. Yeah. Okay. You can tell me if you can't, but I'm thinking that you're looking right now at question 4, acceleration and direction 1, about an Audi and a Buick and a Camry, right? I'm going to sort of just talk through this, maybe a little bit quickly. So like, write things down, please, but I'm going to just try to talk so that I don't get bogged down. But so you've got this Audi that's driving to the east. You got a Buick that's driving to the west, and things happen. And then you got a Camry that's driving east, and different things happen. And you got a dirt right that's driving west. Okay. So everything is still one-dimensional. Everything is one-dimensional. It's an x-axis. It is our job always. I'm so psyched. There's so many videos. Okay, it's our job. It's our job to pick a positive direction and a negative direction. It can be either one, but we have to make a choice and we have to stick with it. I'm going to say, and you could say in your homework, or if you're writing things down, I'm just going to declare, because I think it's the most intuitive for me, that everything that goes east is positive. Everything that goes west is negative. So if I drew a number line right now, all the numbers to the right would be positive and all the numbers to the left would be negative. Okay, now that includes all positions and anything that's happening. Like if anything is heading to the right, that's called positive. Okay, so we're going to see that in a minute. All right, so I'm calling, so that's my answer to A, is I'm calling positive right and I'm calling negative left. Now, then it says part B, given the choice you made in part A, write down the initial and final velocity of each vehicle using negative and positive signs. And, by initial, you mean the beginning, and final mean at the end. Okay. So I'm just going to say these answers. I'm going to try. The Audi, wait, does it say that they start off from rest? I assume they all start, it doesn't say, but I assume they all, well, I assume, oh, no, I'm sorry. Okay, sorry. So for A, so the Audi, its initial velocity is positive 10. Its final velocity is positive 50, right? Because it's going east. It's originally going 10 meters per second going east. Its final velocity is 50 meters per second going east. So the initial velocity for the Audi, like V naught, is positive 10. The final velocity is positive 50. Fine. The initial and final of the Buick is its initial velocity for the Buick is negative 10, right? Because it's going west. Its final velocity is negative 50 because it's still going to the west, but it sped up to a speed of 50. So its final velocity is negative 50. I hope that's clear. Everybody stop me if that's not clear. I mean, this is the point of this thing. Then the Camry, its initial velocity is positive 50. Its final velocity is positive 10. The dirt bike, its initial velocity is negative 50. Its final velocity is negative 10. Okay, now, and here's the point of the whole question. This is the thing I was saying last week, but now we're putting numbers to it. It's asking for the average acceleration of each of these vehicles during the 10 seconds. Now, how do you figure it out? You use that equation, that definition that we've been using over and over that we just used a minute ago. I'm not going to write it down. I'm going to trust that you can. So we're just plugging in the numbers, but we're watching our negative signs super carefully here. The whole point here is the negative signs and what they mean. So I'm going to tell you the answers. The average acceleration, and please stop me. I mean, this is the point. If you like all the answers and you get it, then we're totally going to move on. Because I don't want to bore you, but please stop me if you don't get any one of these answers. You should not be embarrassed. The point of this question is that there is something sort of tricky about it. So don't be embarrassed if any of the answers I tell you now don't sit well with you. And I really mean that. Also, I've been talking so much, it would be good to get feedback. So you can even put in the private chat, it's fine. Or we'll live stream it and then 10,000 of you can put in the, anyway, whatever. So here's the accelerations. I think the Audi has an acceleration of positive 4 meters per second squared, positive 4, i.e. 40 divided by 10. And where to get 40, I mean literally 50, like positive 50 minus positive 10 all over 10. So it's positive 4 for the Audi. Stop me if that doesn't make sense, but I think the Audi is an acceleration of positive 4 meters per second squared. Every second on average, it is speeding up by 4 meters per second. Okay, that's the Audi. The Buick is accelerating at negative 4 meters per second squared. Negative 4. Ultimately, because it's right? Yeah, because its final velocity is negative 50. Its initial velocity is negative 10, right? And negative 50 minus negative 10 is the same thing as negative 50 plus 10. So, and all of that is divided by 10 seconds. So its acceleration is negative 40 divided by 10, i.e. negative 4 meters per second squared. I'm pausing on that. I mean, I will go on a moment, but I'm pausing on saying that the Buick is negative because I want, and maybe the math is obvious. Like when you write down the equation, hopefully maybe you're like, yeah, duh, Yavril, move on already. But the thing that I'm pausing is if the math makes it sort of obvious, but then step back and look, what we're saying is the Buick has a negative acceleration, even though it's speeding up. Right? That's like really the point we're just trying to drum in here, that negative acceleration does not have to mean slowing down. And also in physics, we don't have the word deceleration, right? Like everything is an acceleration because anything is a change. And sometimes changes are positive and sometimes they're negative. But negative doesn't have to mean that you're slowing down. That freaking Buick is speeding up, but its acceleration is negative 4. Why? Because it's speeding up while moving in a negative direction. Okay, so again, stop me if you don't like, I'm looking at the chat. I think I'm looking at the chat. But then the next one, if you get that logic, then you'll get the rest, I think. The next one, the Camry is negative 4 meters per second squared, because that one is slowing down while in the positive direction. Also, another way to put it, why the Buick and the Camry both have an acceleration of negative 4, because another way to put it is their velocity numbers are both going down. They're both decreasing their velocity for 2 different reasons. One of them, the velocity numbers are getting decreasingly positive, so to speak. And the other one, the velocity numbers are getting increasingly negative, so to speak. But if you just look at that number line, in either case, their velocity numbers are like heading to the left. Okay, so it's the Camry is negative 4. And then finally, the dirt bike is positive 4. Even though it's slowing down while going in a negative direction. So it's positive 4 meters per second squared. That's the answer to those. it's meant to just, and hopefully I've just discussed the relationship between speeding up, like part D is what I've just been doing in English. I'm assuming that if you do get it, you totally want me to move on. So I'm going to move on. We've got 10 minutes. But again, if you don't get it, that's fair. Don't be embarrassed. Let me know. But if you do get it, but assuming I'm not hearing from anybody, I'm moving on because there's nothing in the chat. Right. Okay. So then, having said all that, I do think question 5, the one that's on your screen now, I do think question 5 is then kind of redundant. Like I'll mark your homeworks, whatever. But I think question 5 is all about the same issue. And I think you get it now. So I'm going to now go, and we have 10 minutes. What I think is a really interesting, important question is question 6. Hopefully you can see in your screen. Yes. Okay. Question 6. I will ultimately write something down about this, but let's start discussing it right now. Okay. I'm seeing the time. We have these random sets of numbers. This looks like a digression. It just looks like a question about numbers, but it really is ultimately a question about instantaneous velocities and accelerations. In your mind, if you want to make this more interesting to yourself while you're listening to me, imagine that each one of those numbers represents a velocity, right? Like 1 mile per hour, 2 miles per hour, something like that. And imagine that each comma is like a time interval, right? Like, so that first set of seemingly random numbers or seemingly like abstract numbers represent some kind of motion. Like first I'm going 1 mile an hour, and then 1 meter per second. And then a second later, I'm going 2 meters per second. And then a second later, I'm going 3 meters per second. Imagine that the intervals are all seconds and all the velocities are meters per second. Okay, then first it just asks you to get the average of each set of numbers. In the interest of time, I'm going to tell you the answer, and I'm sure it won't surprise anybody. So I'm going to just read the answers, okay, and stop me again. But I think the average of the first set of numbers is 4. I think the average of the second set of numbers is 7. I think the average of the third set of numbers is 9. Now, by the way, I mean, how am I getting these? Well, in principle, I'm adding them all up and dividing by the number of numbers. I mean, some of us can do that faster than others, but if in order to do this work, you added up all the numbers and divided, you're definitely doing the right thing. There's nothing wrong. I mean, that's the safest, smartest thing to do. And just in the first case, like, yeah, I mean, I think 7 plus 6 is 13, plus 5 is 18, plus 4 is 22, plus 3 is 25, plus 2 is 27, plus 1 is 28. Divide by 7, you get 4. So it's that number 4. Okay. So in principle, in my head, that is what I'm doing for each one of these. The average number for the first is 4. The average for the next is 7. The average for the next is 9. The average for the next, I believe, is 27. Now, of course, adding up all those numbers and dividing all those by 7 takes a little while. Either I've done this many, many times, or I have some trick or something. But I think you'll find if you add up all those numbers in row 4 and divide by 7, because there's 7 numbers, you'll get 27. Now that next one, I think that the average, and stop me if you disagree, by the way, because maybe I'm going a little fast, but the next one, I think the average is 11. Yeah, I think it's 11. Stop me if you disagree for the next one. I think it's 11. And now for the very last one, this one I can't do so fast. This one I'm going to have to take out my calculator and break my voice. I mean, I see a pattern in those numbers, certainly. I'd like to do something kind of fast, but I don't think I can do this one so fast, and I don't even think I remember. I think the average for this one is about, could it be 20? I think the average for this one is 20. Actually, I would like to know, disagreement or agreement. Can anybody put in the chat whether they agree or disagree with any of these, but particularly that last one? I think the average of the last one is 20. I would love to know in the chat if anybody. Oh, I'm losing people. This means I've really bored everybody. Oh, cool. Thank you, Alyssa. Alyssa just got, and thank you, Soad. Oh, and I shouldn't have responded until I got more. But yeah, okay, cool. And you're both talking about that last one. Okay, Alyssa and Soad. So going one screen. And does that mean, by the way, Alyssa and Soad or anybody else, do you agree with all the other ones I said too? Is that fair? Yeah, cool. All right, thank you. Oh, and thank you, other people. Yes, really, when I do this, it's a mistake of mine. Even if I'm acknowledging Alyssa and Soad, like, don't others of you think, oh, I just missed my chance. Like, the more people can respond, really, the better for all of us and me, and you get points. Like, your chance doesn't go over just because somebody responded. And I shouldn't really say if they're right or wrong that quickly, but cool. All right. So thank you, Lakshmi, and thank you, Soad, and thank you, Alyssa, and thank you, Soad. I said, all right. So now here's my point. It's 12. I've got 5 minutes. Here's the thing. I hope everybody, you can get the average to each one of these by adding up all the numbers and dividing by 7. You can. And I think most of us probably did. But I think you could see when I was going through these, I did the first 6 in my head, right? I didn't, and it's not because I can add and divide that quickly. Like sometimes I can, but no way did I add up 12 and 17 and 22 and 27 and 32 and 37 and 42 and divide by 7 in my head like that. And I'm sure you could see that. For the first 6, I used a trick. And I'm sure many of you, and I'd love to have a discussion about this, but since we're out of time, I'm just going to say it. For the first 6, I used a trick to get the average, which I'm sure you can see if you got the right answers. The 7th one, I could not use that trick. I literally did have to go to my calculator and add up all the numbers and divide by 7 on that last one. And yes, as you may be noticing, it's because there's a pattern in many of the numbers, but not the 7th one. But let me now be very, very clear. Again, I think some of you noticed a lot of things when you were doing this, but I want to make clear what you noticed. All of those numbers, in some way or another, have a pattern associated with them. I mean, that 7th one, or I keep saying 7th, the 6th one, the very last list, it certainly has a pattern. Like, and it's an important pattern for what we're doing, actually. It's the perfect squares. You might even have noticed that pattern in lab number 3 with the bolts on a string and stuff. Like, that is definitely a pattern. And there's some kind of trick I could do with that pattern. But that's a complicated enough pattern that it doesn't fit all the rest. The deal with all the rest, including even list number 5, even list number 5 looks like it's jumbled, but list number 5, the numbers are just put in a funny order, but it doesn't matter what number they were presented in, because as you all know, when you average, you add up and then you divide, and adding is commutative, right? So even in that 6th list, even in that 5th list that says 8, 6, 10, 12, 14, 16, I looked at it and I'm like, all right, someone's trying to trick me. You know, they put the numbers in a funny order, but I can rearrange the order however I want. And I can see that what's really happening there is 6, 8, 10, 12, 14, 16. And I can see that it's therefore just like all of the lists before it. And what do all those lists have in common? Here's the key point, and here's the point about motion. And I know, like everything else, I think a lot of what I'm saying is probably obvious to some of you in a way, but I think like the last bit of it is maybe not obvious. What you notice about all those lists, even including number 5, like once you arrange order, is that all of the numbers are increasing or decreasing by a constant amount, right? Like they're evenly spaced. Like even if the numbers are changing, they're always changing by the same amount, not the last one. The last one is some kind of pattern, but like the change from 1 to 4 is 3. The change from 4 to 9 is 5, not 3. And the change from 9 to 16 is neither 5 nor 3, but in fact 7, right? I mean, there's a pattern of the pattern, but in that last one, you're not always increasing or decreasing by the same amount. In all the other ones, you are, and here's my point with only 2 minutes left, the thing to notice, and I'm sure you did, I just didn't have time to open up for discussion. In all the others, when the numbers are changing by a constant amount, the average is the middle, right? And it makes sense because if they're all changing by the constant amount, then the middle numbers literally is the middle. Like all the numbers below it are less than it by the same amount as all the numbers above it are, because you're always changing by the same amount. Let me go a step further. When I say that the average is the middle, which I'm literally saying, I'm saying from here on in, when numbers are changing by a constant amount, the mean is the same as the median. Let me be more specific. I'm saying when velocities are changing by the same amount in time, i.e. when acceleration is constant, then the average velocity is the average of the velocities. That's what I'm saying. I'm saying when velocities change by a constant amount, when the acceleration is constant, then the mean velocity is the same thing as the median velocity. The average velocity then, and only then, is the same as the middle velocity. And let me take it one step further. When I say middle velocity, look what I really mean. This you might or might not have noticed. Look at that first list. When I say the average of the whole thing is 4, which is the number right in the middle, what do I really mean by middle? I mean I could just ignore that. As long as I believe in the pattern, I could just take the very first number 1 and average it with the very last number 7. I could take 1 plus 7, I get 8, divide by 2, 4. right? Look at the next one. 4 plus 10 is 14. Divide by 2, 7. This is a deep point now that you might not have noticed. I'm saying that when the acceleration is constant, when the numbers are changing by the same amount, in order to get the average of the whole thing, all you have to do is average the very bottom with the very top. All you have to do is average the first and last, and you'll get the middle, which is the average for the whole thing, as long as, if and only if, there's the last thing I'm going to write, but this is an equation now, there's the last thing I'm going to write, and then we're going to go. But I'm saying we just learned something about accelerations here. Whoop. We just learned something about accelerations here. Yeah. And it's this. What we learned is when, well, I should say, if and only if acceleration is a constant, when numbers are changing by the same amount, then the average velocity of a whole thing will be equal simply to the average of the first and last velocity. This is a third equation for, oh, you can't see. Why can't you see the screen? Wait, you can't see the screen, can you? I don't understand. Wait, why can't you see the screen? Hold on. Hold on. And I know we have to go. And we will go. I just want you to see the equation on the, why? Okay. Why is it not? Okay, here it comes. I'm saying this is our last. Why is it not? What is going on? I don't know why it's not. Well, and if you have to go, you have to go. I'm saying the equation is this. If and only if A equals A naught, I don't understand. When A equals A naught, what is it sharing? When A equals A naught, V bar equals V naught plus V over 2. We'll write it again. Well, you'll see it in the notes when I publish it, but I don't know why. I'm saying we spent all this time, and then we're going to go. I see it's 12:06. We spent all this time at the beginning of the year saying average velocity does not mean the same thing as average of velocities. It's true, it doesn't mean the same. But when acceleration is a constant, you can get average velocity by simply averaging the first velocity with the last. When and only when acceleration is a constant, you can get average velocity for the whole by averaging the first and the last. You can go goodbye. I'm going to hang out for 1 minute and try to share this screen probably for anybody who has another minute to see it. Yes, but have a good day. Sorry to keep you, and I'll also hold for questions. But yes, so that's our third equation though. V bar equals V naught plus V over 2. Now, why is this? Thank you. And yes, do please go if you have to. Try again. Okay, there's that. Now we go. Okay, that's the equation I'm trying to say. That's our third equation in this course so far. If and only if A equals A naught, then V bar equals V plus, and that is an equation. No, and we're still saying V naught triple equals sign. It's now a new way to get average velocity. When it always equals its displacement over time, what it equals in special circumstances is the average of velocities. That's it. So I'll just pause for questions, but thank you guys so much. Sorry. Thank you for your patience. Okay. Thank you. Okay, thank you. And Daniela, you're good? Good. And thank you all.